Okay, welcome back, everyone. It's my pleasure to introduce this week's speaker, George Papadopoulos from King's College London, who will speak to us today on the rigidity of special and exceptional geometries with torsion of closed three form. So please, George.
Oh, thank you very much for your kind invitation, Jeff. I will be talking about a paper that I wrote back in November last year. Um, um, so the geometries that I will talk about are geometries that the Riemannian geometries that they have a natural, let's say, three form that can be used as a torsion to construct a connection with torsion. So you have an n-dimensional manifold. G is the metric, 3 is the three form, and then you define this connection with a hat, which is the Letzevida connection plus this combination of H with the inverse of the metric. I mean, I write down here in coordinates, so there is no, let's say, confusion about what it is. And there are manifolds that they have a natural such connection. I think the simplest example of such a manifold is as the Hermitian manifolds, where you have the manifold, the metric, and a complex structure. So the complex structure squares to -1 to minus the identity naturally, and the metric is Hermitian. That means satisfies this condition here, where x and y are vector fields. The Hermitian manifolds actually admit several compatible connections, and I will explain what compatible means in the next page. But there is only one for which the torsion is a three form, and it's given in terms of the Hermitian two form omega in this particular fashion, where you take the exterior derivative of omega and you take the inner product with a complex structure and you adjust the signs and you get a three form, and this form actually is the torsion of the connection. And the Hermitian two form is defined in this way using the metric and the complex structure. And compatible means that actually the metric and the complex structures are covariantly constant with respect to this connection with torsion. Of course, typically a connection, a metric connection, has holonomy contained in ON or SON. In this particular case, of course, because you have an additional covariantly constant tensor, the complex structure, and the holonomy is included in UK, in the unitary group. And in general, in this kind of geometries, typically you get the torsion is not closed. If you just pick a generic Hermitian manifold, you do this calculation, you find that actually DH is different from 0. But if it is closed, then the Hermitian form is actually DD bar closed. And that's actually a very interesting property to have. Now, if you take the Hermitian manifold and you somehow consider it with respect to this connection with skew symmetric torsion, then typically you say that you have a Keller manifold with torsion or KT manifold. Now, another class of manifolds that I'm going to talk about, apart from KT ones, are the KT ones that, in addition, the holonomy of the connection with torsion is included in the SUK group rather than the UK group, and so these are kind of generalization, let's say, of Calabi-Yau manifolds, so they be called Calabi-Yau with torsion. Such definitions, of course, can be extended to manifolds with more special structures, and another class of manifolds that I'm going to talk about are what I call hyperkeller with torsion. One starts basically for a 4Q dimensional manifold. It has three complex structures that obey the algebra of imaginary unit quaternions. So we obey this algebra here. And the metric G is Hermitian with respect to all three complex structures. So I call them trihermitian sometimes. And then on top of that, you say that this trihermitian manifold admits a hyperkeller with torsion structure, HKT structure, if and only if there is a compatible connection with skew symmetric torsion. So, what happens is in the Hermitian case, you get one for sure, but it's just, you don't have to impose any other conditions. But here to say that there is a connection with torsion imposes actually an additional condition on the trihermitian structure. And of course, this can be generalized, and there have been works on that, on G2 manifolds with torsion and spin 7 manifolds with torsion. Although in the title I suggest that I'm going to talk about all these cases, but actually I will talk about the very simple case and then go to something else. And also there is also quaternionic manifolds with torsion. And these are actually relevant, but I managed to avoid in the talking about them to make things a little bit simpler. And then sometimes in some terminology goes as follows, that in general, of course, as I said, the torsion is not zero. If you just take a generic Hermitian manifold, you will see that actually you calculate the H, you will find that actually this is different from zero. But if it is actually the free form is closed, sometimes the corresponding structure is called strong. So I'm going to use the terminology a little bit later, so I introduce it. Now, why on earth is interested in this kind of structures? Well, there are several reasons for that. As I said, for Hermitian manifolds, admit automatically a KT structure, so that's good. And now there's a big subject in mathematical physics that all these kind of structures, especially the KT, Calabi-Yau with torsion, and HKT structures, have to do with a number of supersymmetries that sigma models have in various dimensions. The whole subject actually started some time ago by Zumino, that observed that if you look at 4-dimensional sigma models, then you have to require that the target space is scalar, and then from there, in 2 dimensions, you get more rich structures. For 2-dimensional sigma models, you get more rich structures that include torsion and so on. The Calabi-Yaus with torsion manifolds appear in string compactifications, which is another topic in string theory. And there's some try to okay. And then there is the other spaces that they have this kind of structures. Sometimes it was surprising to realize some years back that if you look at the moduli space of black holes, typically 5-dimensional black holes and brains, then they exhibit an HKT structure. And that actually gives a lot of examples of HKT metrics in all four Q dimensions. But another area that this kind of geometries appear, actually it is related somehow to a little bit to these supersymmetries in sigma models, but it's got the relation rather tenuous, so I'm not going to explain it. It is the moduli space of istatons over Hermitian and HKT manifolds, 4-dimensional Hermitian HKT manifolds. It was demonstrated actually.
Wait, sorry,
that
George, can I
sorry?
Are these black hole moduli spaces ever complete?
Yeah, I think they are. Some of them they are complete. Yeah, but they are not compact. I mean,
and are they ever
not compact.
strong?
Yeah, yes, some of them are strong, but some others are not.
I see. Okay.
In fact, what happens is that this is related in a tenuous way to the to this KT and HKT structures in 2-dimensional sigma models. In 2-dimensional sigma models, you have to take H to be closed.
Mm-hmm.
But if you look at the 1-dimensional sigma models, that they have target spaces to these moduli spaces of black holes. Actually, you don't have to take H to be closed. In this case, actually, is realized in a certain class of 5-dimensional black holes. So you can have moduli spaces with closed torsion and a moduli space of black holes with no closed torsion.
I see. Okay, thank you.
But actually, another area that that this kind of geometries appear, it is in the moduli space of Isotons over Hermitian manifolds and HKT manifolds. It has been known for a long time that if you take Isotons over Keller manifolds, then the moduli space of Isotons is Keller, at least the smooth part. And then if you take Isotons over hyperkeller manifolds, then the moduli space of Isotons is hyperkeller manifold. And then it was realized actually that if you take the modular space of Isotons over Hermitian manifolds, which are not necessarily, they don't necessarily have a closed torsion 3 form, nevertheless, the modular space admits a strong KT structure. That means the 3 form of the modular space is closed. And the same applies for the HKT case. So this is another source of examples, I guess, that give examples of strong, this time, HKT and KT manifolds in all dimensions. Well, where the modular spaces exist, by the way. So, and another area that now this have found applications is now in kind of more recent idea of generalized Ricci flows, where Calabi-Yau with torsions and HKT manifolds can be thought as steady solitons in this context. So, and actually this is relevant to what I'm going to talk a little bit later. But having said all that, if you look at the literature, you will see that actually there are very few examples of Calabi-Yau with torsion and in fact, none. Well, not really none of the interesting type. Very few examples of Calabi-Yau with torsion and HKT manifolds for which are not products of some group manifold times a Calabi-Yau or hyperkeller manifold. And the question came up whether actually there are any, especially for the HKT case. So, so part of the idea is to try to address this question as much as I can, as you will see later in the talk. Okay, so bearing in mind that it was difficult to find examples, then people thought of putting some simplifying assumption, and the simplifying assumption that was put, okay, let's consider manifolds for which not only H is closed, because I'm talking about examples with closed torsion, strong. When I said here, I meant compact, strong Calabi-Yau with torsion and strong HKTs, because if you remove the closure condition, it's fairly simple to write lots of examples. So people thought, okay, let's put a simplifying example assumption. Let's assume that the 3 form is closed and also parallel with respect to the connection with torsion. And the question is, can we now somehow find an interesting examples of such strong, let's say, Calabi-Yau with torsion and HKT manifolds? Well, what I'm going to demonstrate actually before even one puts any additional structure on the manifold Mn like KT or HKT, actually just as a Riemannian statement, in general, actually the manifold is locally a product of a Lie group times a Riemannian manifold, and the support of the torsion it is in the group. So you get typically only, actually you get a semi-simple Lie group that has the connection with torsion naturally, and then times a Riemannian manifold that the support of the torsion on the Riemannian manifold vanishes. Moreover, if the manifold you start with is complete and simply connected, then it is globally a product. It's just the de Rham theorem, really. And of course, this kind of examples, this kind of structure has been observed now also in the, well, actually this is as well derived before, on the KT for KT manifolds, Calabi-Yau with torsion H, KT, G2, spin 7, and so on. But then this kind of result in the grounds or Riemannian geometry kind of simplify all the other proofs because you get factorization before you even begin putting the additional structure. And the second theorem that I'm going to try to explain or to talk about is, okay, failing, let's say, to achieve something non-trivial. I mean, of course, the group manifolds are not trivial, but I'm not saying they are trivial per se, but something that is not a product. Let's focus on the 8-dimensional manifolds and try to see whether actually we can have a compact, strong 8-dimensional non-hyperkähler HKT manifolds. Now, if I will say that this, I will look at the case where actually these manifolds admit the action of the Lie algebra U1 plus SU2, but actually it's not such a strong assumption, this as I'll explain. And then I will make the assumption that this actually action can be lifted to a free SU1 times U2 action. I write it like this because I could put U2, but then you will see why I write it like this. And that in addition preserves the span of the 3 complex structures that the HKT manifold has. Also, this is not a very strong assumption either, as I will explain. Now, if the space of orbits of this group action is simply connected, then I will demonstrate that actually M8 is differomorphic to SU3. So this is another rigidity result that shows how constrained this manifolds are. I can do a little bit better if I assume that actually this Lie algebra action lifts freely to a U1 cross SO3 free action. I have that at the end of the talk. If there is time, I will go through it. There's another possibility that you don't get an abelian action here, but you get the action of an abelian Lie algebra, which is 4 copies of U1. And then if this can be integrated to a torus T4 action, then actually in this case you can prove that the manifold actually is again a product, locally isometric product. So again you go back to what we have here pretty much. So let's try to give a kind of outline of the proof of this statement first, and then I will prepare slowly the ground how one can go about improving the second theorem to see how it goes. Okay, in the first, I begin with proving basically 2 Bianchi identities for the connection with torsion. The first one is pretty well known, and is also responsible for a lot of statements regarding parallelicity with respect to the connection with torsion in various occasions for special structures. I'll come to that a little bit later. But this one, it has not, I think it has not been observed in the literature, although it was known to me anyway, but maybe not very well known. And in what it says, I mean, this is a physicist notation about taking the skew-symmetric part of J, K, and M, and the same here. It says that if you skew-symmetrize the last 3 indices of the curvature of the connection with torsion, you get this identity here. And then if you skew-symmetrize the first 3 indices of this of the curvature of the connection with torsion, you get this identity here. Moreover, it's known that if the torsion is closed, which is the case we're interested in, then you can flip around the indices, the pair of indices Ij and Kl in this way, and then you get from the curvature of the connection with torsion H to the curvature of the connection with torsion minus H. This is the check. The check curvature is associated with the check connection that has torsion now not H but minus H. Now, in the second, now from these identities here, I think one can guess how it goes, because if you assume it's closed, these terms here disappear. And then, of course, we assume that in the theorem 1, that the torsion is parallel with respect to the connection, to the Hatted connection with the torsion. So, and then what I would demonstrate that these two imply that actually the 3 form is parallel with respect to the Civita connection. And in fact, H satisfies the Jacobi type of identity. So the proof begins that if H is closed, then I calculate now the covariant derivative of the torsion with respect now to this connection here, which has torsion minus H. But this is exactly, I use this identity here because when I flip the sign of the torsion, the same identity applies, but one has to flip the sign here, the connection here, and the sign here. So you get this, but then of course from this identity here, I can flip around the pairs of indices, so I get that. But this here, the curvature with the Hatted curvature, of course, is 0 because of this identity here. And therefore, you find that actually, if you assume that your torsion is closed and it's parallel with respect to the connection, the Hatted connection with torsion, then it is also parallel with respect to the connection, the Čech connection, which has torsion minus H. And of course, the two statements together imply first that actually is parallel with respect or covariantly constant with respect to the Civita connection, and also satisfy the Jacobi identity. So that gives you a very strong indication that you end up with something which looks very, very, very close to be a group manifold. Okay, and then the proof of the theorem goes, well, you construct the quadratic form by taking the inner product of these two forms here, which is the 3 form, taking the inner product with respect to the vector fields B and W. And then, of course, since the metric and H are covariantly constant with respect to the Civita connection, automatically this quadratic form is in fact covariantly constant as well. Then the integrability condition says that the holonomy of now the Civita connection will reduce from a potential SO to N to a product of SO and alpha, where N alpha here is the multiplicity of the eigenvalue lambda alpha of this quadratic form. This can be always be diagonalized as a symmetric tensor. So then of course that automatically implies that the manifold is locally isometric to a product. And then of course if M is simply connected and complete, then it's globally a product of other manifolds. Let's see now how H decomposes under this decomposition. There are two possibilities that none of the eigenvalues of lambda alpha are in fact 0. In that case, this would be the killing form, let's say, of a Lie group, which is now non-degenerate, and therefore locally M is a semi-simple Lie group. And since all Lie algebras, they define a Lie algebra structure, of course, because H satisfies the Jacobi identity, automatically defines a Lie algebra structure, and then of course every Lie algebra has a unique simply connected group associated with it. So M can only be that group divided by some discrete subgroup. So this is locally, in fact, all these manifolds are group manifolds. Now, the other possibility is that one of the eigenvalues here is 0. So let's split locally the manifold to some n 0, which corresponds to the 0 eigenvalue times the rest. Now one can observe that actually the Lie derivative of the 3 form along any vector field which is in the direction of n tangent to n0 is automatically 0. So that means that H has support only in this part here of the manifold. And moreover, the inner product along any such vector field is also 0. This follows from this because if we take V to be tangent to T tangent to N0 inside the manifold, then of course, because it is a 0 eigenvalue, this will vanish. That will imply this is 0, and therefore so the 3 form is always carried by the part which is not in the 0 eigenvalue of the decomposition. So that means automatically that this part here is again locally a Lie group, a semi-Siebel actually Lie group, and therefore the manifold M is a product of some Riemannian manifold which where the torsion vanishes or the 3 form vanishes times some semi-Siebel Lie group. So all these manifolds, in other words, are products, and of course, if you have this information in the Riemannian setting, then you can simplify a little bit the proofs that were given in the literature for the cases that they have additional structure. In a sense, if there is a conclusion here, it is a conclusion that if you impose that H is covariantly constant with respect to the connection with torsion, is way too restrictive to get examples which are not products. I think that's the conclusion. So the only thing that remains to be done is to one should try, in other words, to remove this condition, because in an effort to try to find more general examples. And now, before I go and do that, I will explain the strong HKT structure on SU3, and there is a reason for it, as you will see. This was done a long time ago, actually, by these people, and then if you take the Chevalier basis in SU3 or in the Lie, I mean, it's a Lie algebra calculation, so because as soon as you do in the Lie algebra, you cannot just parallel transport it either with the left or the right action throughout the group manifold. So I will just do a Lie algebra calculation. So these are the HPs are the two bases in the Cartan subalgebra. E alpha and E beta are the step operators associated with the simple groups. And then you have also a step operator or a step generator associated with the highest root, which is alpha plus beta. And then you have the negative roots, and that's the basis, the Lie algebra of SU3. There is also, of course, an inner product, which is in this basis is defined like this, where gamma now stands for every positive root. That means stands for alpha, beta, or alpha plus beta. Now, the idea is to try to give what are the complex structures are for this HKT structure on SU3. Actually, the Chevalier basis is actually the complex basis in some ways. In the first complex structure, the complex structure takes the H1 to H2, and of course, when you square it, it tells you how it acts on H2, and then acts on the basis of the positive roots and gives you I back the generator of the positive, or labeled by the positive root, and similarly for the negative generators of the labeled by the negative roots. The second complex structure is more interesting. You get this is defined like this. I'm not going to describe it, it's pretty obvious. And then you can prove actually that both I and J are integrable and anti-commute. Now, furthermore, one can consider the vibration. I think there's here, that's why I use U1 times SU2 S. That means the whole thing as determinant 1 is a special, because I want to embed this inside SU3, and then I cannot do it otherwise, at least not in a natural notation. So that's why I wrote it like that. Actually, the group is isomorphic to U2. And then if you see there are different embeddings actually of SU2 in SU3 labeled by the positive roots. So there are 3 different embeddings. But if you want to get something nice, that means this vibration structure to be in a sense compatible with the complex structures. In other words, the fiber group to rotate the complex structures in a nice way, you have to pick this particular embedding associated with the highest root for this choice of complex structures. If you don't make that choice, then they don't preserve the plane of complex structures and would be rather complicated. It gives a much more complicated structure. So if you do this, then you will see that actually this particular embedding obeys all the properties of the theorem 2, all the assumptions made for the theorem 2. And so this provides a kind of example that actually the content of theorem 2 is not empty. And it's nice to, when you do calculations later on, it's nice to have this example in mind, because it has several other ingredients that I'm not going to mention, which also ties up with the structure that I'm going to present later. Okay. Now, I give you an outline how I'm going to try to prove theorem 2. First of all, I will explain why for the HKT manifolds, the 8-dimensional ones that I'm interested in, they admit the action of the U1 plus SU2 Lie algebra, which are generated by covariantly constant vector fields. And I will just try to argue that this assumption is not a very strong assumption. The next step, I will try to explain that actually if you have a vibration like this, if you lift this Lie algebra action to a group action, to a free group action, and you have a principal bundle type of vibration over 4-dimensional manifold B4, which is the space of orbits of this group action, then actually B4 is an Adishev dual 4-manifold with positive scalar curvature. This is key in what is going to for the proof, and in particular it has to do with a theorem by Lebrun, which says simply connected Adishev dual 4 manifolds with positive scalar curvature are actually homeomorphic to either S4 or to the connected sum of k copies of CP2 bar. Now, I have to explain a little bit why I take CP2 with the opposite orientation. The reason that I do that is that in the literature, typically people take the orientation associated with the standard complex structure on CP2. But here you see the orientation I pick is the orientation that I inherit from the complex structures here, the ones that I have on the HKT manifold. And this naturally, so if I declare this to be, I take the orientation with respect to this, automatically it's exactly opposite from the standard orientation that is given on CP2, and that's why I get CP2 bar. So I get the connected sum of k copies of CP2 with opposite orientation. So this in other words will control the structure of the base manifold a lot. Actually, the homeomorphic here is not true for small k. Actually, they are differomorphic, but it's a kind of thing that I'm not going to use much. And now the next step is to observe that that the closure of the three form implies that the Pontryagin class of this vibration must be the first Pontryagin class of this vibration must be trivial. So so that gives you an extra topological restriction on the base space. And I will explain that how this can be used to argue about the various outcomes. Now, a similar proof now can be constructed if this Lie algebra action lifts not to SU1 cross SU2, U2 altogether special, but to U1 cross SO3, which is another possibility. I'll have some slides on that. I will explain how this works, and some surprise at the end. And also what I'm going to say about this case here also applies to U2 because of this relation. So it's no different if I had assumed here actually a U2 vibration, but I had to explain the inclusion a little bit more. Okay, so these are the steps of the proof. So let me go and try to explain how that works. Okay, so let's begin now with the let's kind of diversion. You see, for people like me that sort of I was before the Perelman work and the generalization to the generalized Ricci flows, most of us assume both this condition and this condition here. I'll explain. So if you have well, the definition is you have a manifold with a metric and a three form. A generalized steady soliton is if there is a vector field X on the manifold, that the Ricci tensor now of this connection with torsion is equal to the covariant derivative of X with respect to the connection with torsion. And here, basically, X must be one form, but I distinguish not between vector fields and one forms. Otherwise, the notation would be even more complicated. So from the context should be clear what it is what every time. Now, the same manifold actually is a generalized gradient soliton if there is a function such that this equation is satisfied. Now, in the past, you see this equation is famous in string theory because these are the so-called string field equations, and people have studied them extensively, of course, within string theory. This equation was also known actually in the context of sigma models, because that tells you that the sigma models are scale invariant, some kind of property in quantum theory. But it was never thought at the time that this implies that. But here is the beauty of it, that actually, if the manifold is compact, then this equation implies that, and the compatibility of the two, which is a very beautiful proof, by the way, based on the invariance of functional. This implies that if you take the difference between these two and eliminate the Ricci tensor part, then you get that this vector field Y must be covariantly constant. If it is non-zero, that means with respect to the connection with torsion. Now, as soon as you have a non-zero tensor which is covariantly constant with respect to your favorite connection, automatically triggers a reduction of the holonomy group of the connection. And it's a kind of very strong property on the manifolds. Now, if you have a strong HKT manifold, you can prove that actually that it is a steady soliton. And the vector field X that sits here is the Lie form of the manifold. And the Lie form is constructed out of the, well, you have three potentially Lie forms, which are constructed out of the Hermitian two form omega with respect to any one of the three complex structures. and taking the inner product with respect to the complex structure as well. So you get in one form out of this, but potentially there are three, but actually it turns out that for HKT manifolds, all the three Lie forms are the same, so that you have one at the end. And this one form plays the role of X in this relation here. And this is a consequence actually of the first Bianchi identity that I mentioned in the beginning of the talk. So that's why this Bianchi identity is so important in the discussions. And of course, so if the HKT manifold is compact, there must be some function phi for which this combination here, the Lie form plus 2, the exterior derivative of the function phi, is parallel with respect to the connection with torsion. So this is this is one of the results coming from a different, seemingly different direction from the one that I started with. Now, if so happens that this is true, if this is covariantly constant with respect to the connection with torsion, then there are two outcomes. One, it is that Y actually is killing, and the other is that leaves the three form invariant. So the Lie derivative of G with respect to Y and the Lie derivative of H with respect to Y vanish. Now, there is always a possibility that actually Y vanishes itself, and so you get none of these properties. But if this is true, then the Lie form has to be the exterior derivative of the scalar of the scalar function f. And this kind of class of HKT manifolds are known as conformally balanced. And there's some paper that I wrote a long time ago with Stefan Ivanov. We prove that actually this kind of manifolds are hyperkähler. So if you want to have a genuine HKT, compact HKT manifold with closed reform torsion, which is not, that means not hyperkähler, you have to have a Y which is different from 0. And that's quite a strong condition, especially combined with the next step, that if Y is different from 0, then it admits 3 more covariantly constant vector fields with respect to the Hutted connection. So you get 4 at the end instead of 1. Now the question arises whether actually the Lie bracket algebra of these 4 vector fields closes or not to the set or not. Well, I mean, there are different ways of thinking about this. One way to think about this is that let's suppose that it doesn't, especially for 8-dimensional manifolds, is quite detrimental, because if it doesn't, then you have a fifth, let's say, vector field. But then you can prove using the first Bianchi identity that I presented, and that becomes again covariantly constant with respect to the connection with torsion. Automatically, that triggers a reduction of the holonomy of the Hutted connection. But then on top of that, you get another 3 by taking this combination here with a complex structure of the 5th vector field. So eventually you get 8. So for 8-dimensional manifolds, automatically makes it a group manifold. So it is in a sense, if you want to get something which is not a group manifold, you better say that actually this algebra of the vector fields closes. So the 4 vector fields close under the Lie brackets. Now, I'm not going to explain this too well, I think, because it's a little bit complicated, but it turns out that if you assume that the Lie bracket algebra on these 4 vector fields closes, then you can prove that the Y, the first one, commutes with the other 3. And then you get this, there are not many Lie algebras up to dimension 4 which they have a kind of positive inner product on them. So this is the possibility, where h here is a constant that I can tune to be 0 if I want to, but I leave it as it is right now. Well, not always, but I will account for two possibilities, either h is 0, h non-zero. And moreover, it turns out that the d derivative of the three complex structures with respect to the y vector field is 0. So this y is triholomorphic. Now there's this extra condition here that says how the complex structures rotate under the action of the three remaining vector fields. Well, again, you can play the same game as for the closure of the vector fields here. If it doesn't, then you automatically get another covariantly constant 1,1 tensor that is going to trigger the reduction of the group, and therefore eventually you're going to end up with a group manifold at the end. So better, it is in your advantage if you want to get something non-trivial, to assume that actually this four vector fields actually leave the plane of the three complex structures invariant, and therefore rotate the three complex structures like this. I mean, there are not many representations you can write down for that. And then there's a possibility also that h is 0, in which case the whole Lie algebra is just 4 U1s. But if it's different from 0, then the Lie algebra is U1 plus SU2, as I said in the assumptions of the theorem. Now, there's a different take, a different explanation for all this in this paper here, which appeared fairly recently. And now, and there are not many actually Lie groups for the Lie algebras that support this kind of Lie algebra. I mean, either you get this group here, the U2 or SU1 times U2 special, or you get U1 times SO3 and for h different from 0, or for if it is abelian, it's just D4. So this is pretty much what you have. So that's so that explains a little bit the why the assumption of the theorem is the way it is, and it's not a very strong assumption actually. Now there is now what well, as soon as you assume now that well, let's assume that now this Lie algebra action of the U1 plus SU2 Lie algebra action gets integrated to some action, some compact group K on your HKT manifold M8. Then you can prove that then you can prove that actually the base space of that vibration admits a quaternionic Keller, is a quaternionic Keller manifold, not quaternionic Keller with torsion, it's just quaternionic Keller, where the metric now here, which is on the 8-dimensional manifold, can be split into vertical and horizontal parts. The vertical part comes basically from the fiber using now the connection lambda, which is a principal bundle connection associated with the vector fields y, given by this expression here using the metric, and something from the base space, which is exponential to phi of the scalar field, which is actually in physics called the dilaton, and the pullback of a metric of the metric G0 of the base space. Now the three form it can be rewritten as a Chern-Simons form of this principal bundle connection lambda plus something that comes from the base space, and try to explain this notation. This is the pullback with respect to the projection map. This is a Hodge duality with respect to the G0 metric here. And this is the exterior derivative of the exponential 2 times the scalar function phi of the dilaton. And moreover, the Hermitian forms of the HKT manifold again splits into some vertical part and some horizontal part, which is related to the Hermitian forms associated with a quaternionic Keller structure here, pulled back on the bundle space. So this is the structure that one gets. But also you have some additional conditions on the connection that basically tells you how the fiber K twists over the base space. And as I said, the Lie algebra is U1 cross SU2. So this is the curvature of the U1 part. And the curvature of the U1 part is on the self-dual. This is another way of saying this, is that this 1,1 with respect to all these complex structures here, to all three of them. Now, the other condition is that if you take now for the remaining three components of the curvature, if you take now the self-dual part, then it is given in terms of the dilaton or the exponential of the dilaton or the exponential of this function phi times the Hermitian forms you get associated with the quaternionic Keller structure here. So this is a structure that you get if you consider that you can integrate the U1 plus SU2 action to some compact group free compact group action on a mate. Now, I also have another piece here.
George?
Yeah.
Are these conditions on the curvature basically coming from like the closeness of H and
it
like
comes from this.
Oh, right.
Okay. Because you see, you can rewrite this in terms of the torsion. And the curvature here and the curvatures here are just components, the horizontal components of the torsion. Okay. And so this is pretty much the inner product of H with respect to the vector field associated with Y and the horizontal part of it. And then that's what the curvature is. Okay. And here is the same. Then you can trace this here and prove that.
I see.
Now there is also this key point here that I didn't mention, and maybe I should have already. I claim that if you take the associated adjoint bundle of M8 viewed as a principal bundle, it has to be identified with the bundle of self-dual two forms on the base space before. Now, a very quick explanation of that is that if you compute the covariant derivative, the Letzivita covariant derivative of the complex structures associated with the quaternionic structure on the base space, you get this piece, and then you get, of course, another piece that involves the rotation of the three complex structures in the standard way that the quaternionic Keller manifolds are defined. Now, this Xi here is the pullback of lambda, really, from M8 on the base space using a local section. So this is basically the connection, lambda, pretty much, and tells you that acts on the complex structure with respect to the adjoining representation of SU2. So this justifies that. And I'm going to use this later on because that gives me the way to do the calculation for some topological calculation. Now, if you say that H is given in terms of the Chern-Simons form for lambda plus something that comes from the base space, given by this expression here, and these are globally defined, then I take now the D of that, then what I get F wedge F plus the d of something equal to 0. Automatically, that tells you that you get a topological condition because this has to vanish up to an exact form, and therefore the first Potriangin class now of the M8 view as a principal bundle over B4 has to vanish. Moreover, one gets a differential condition out of this. Just dualize that, do a little bit of calculation, and you find that the d square with respect, of course, we take now 0 here, or O implies that I consider Lechi-Witten connection with respect to the G0 metric, is given by this expression here. You get a term that depends on the curvature of F0, and then the anti-self-dual part of the remaining 3 curvatures squared, and then you get another piece that comes from the self-dual part of these curvatures with a different power in the exponential for phi from this. I think so I get one topological condition and one differential condition. Now the next step I promised was I have to demonstrate that actually B4 is not just any quaternionic Keller manifold in 4 dimensions. After all of them are, but it actually is an anti-self-dual one. And moreover, the curvature of the scalar curvature of the G0 metric is positive, is strictly positive. Now let's attack this first. This I'm not going to give details, but I'll tell you how one can get it. We know that now the M8 is a steady, is also a gradient soliton, so it satisfies the gradient soliton equation, or the string equation, if you want to use the older terminology. Now you just go here and you rewrite everything using this information here. And then when you do all that, you see here this contains by default R0, because it is one of the many pieces you get out of expanding. I take the trace of this and then I expand the scalar, the R hat curvature scalar in terms of the other fields. I do a kind of longest calculation. Eventually, you end up that you get something that depends on R0 here. But here, this piece here doesn't depend on R0. So the compatibility of this piece here and this piece here really gives you an expression of R0 in terms of the function phi, which is given like this. Now you take this and you plug it in the expression for the self-dual part of the curvature associated with the SU2 part of the connection of the bundle M8, or the principal bundle connection. And then you find this expression here. It tells you that the self-dual part is given by the scalar curvature of the G0 metric times, of course, the Hermitian form associated with a quaternionic Keller structure. This go back to the 4-manifold theory, and in particular, I mean, we can find here there is a theorem in the book by Simon Salomon that says if you get this condition, if you can express the self-dual part, actually for him it was on the self-dual part. So I said there is a problem with the, well, not a problem, but the way the natural way that the orientation goes. This talk is through this quaternionic structure. So if you get an expression like this in terms of the self-dual part of the curvature is related to the scalar curvature and to the Hermitian forms in this particular way, then automatically implies that the self-dual component of the Weyl tensor of G0 vanish. So the manifold B4 is an anti-self-dual 4-manifold. Okay, and now there is a beautiful theorem by Lebrun which is quite nice, that says, well, if B4 is compact, simply connected, and the self-dual for manifold, actually, he was talking about self-dual, but because how to adjust the orientation for the orientation I use, then actually B4 is homeomorphic to either S4 or to the connected sum of k copies of CP2 bar in my case. And actually the fact that you get, you see the intersection form of k copies of CP2 bar is minus the identity. So the theorem basically works because the anti-self-duality condition, together with the positivity of the scalar curvature, kill the self-dual part of the two forms, of the harmonic two forms. Is a nice identity. One of these, I say, which kind of harmonic forms we have. I cannot pronounce the name. It's, I think, probably German.
Weizenbach.
Yeah.
Sorry, George, we're sort of running over.
Sorry, I didn't realize. Yes.
5 minutes or something, or?
Yeah. Okay. Okay. So how much time do I have?
Well, is it possible to wrap it up in maybe 5 minutes, or no?
Yeah, I think probably I will. Yeah, okay. I will do that quickly. Then the whole thing goes as follows: that this kind of bundles with this kind of fiber over 4 manifolds are characterized by a pair of a line bundle and a rank 2 complex bundle. Subject to this condition here on the first CERN class is no surprise, because the fiber group is special. So they are classified by the first CERN class of the line bundle and the second CERN class of the rank 2 complex bundle in H2 and H4 with integer coefficients. Now the triviality of the first Podryagin class, which is the same as the triviality of this class here involved in the curvatures, can be expressed as 3 times the square of the first CERN class of the line bundle plus 2 times the Euler class of the base space plus 3 times its signature class. So now, as I said before, because the fact that the associated adjoint bundle of the principal bundle M8 is the same as the adjoint bundle of E. So P1 of that, the first CERN class, the first Podryagin class of this, is the same as the Podryagin class of that. It is the same as the first Podryagin class of the bundle of self-dual 2 forms on B4, and this is known as twice the Euler plus the signature. Now it's also known that you can express the first Podryagin class of the adjoint bundle in terms of the first CERN class of the bundle and the second CERN class of the bundle in this particular way. So you get a relation between the first class and the second class of E in terms of the Euler class and signature of the base space. Now, after that, you do, I mean, you can do in different ways the calculation, but one way is to just do the splitting principle for E. You write the first class like this, the second CERN class like this, the Podryagin class like this, and then you set L to be the first CERN class of L. And then, of course, this relation here tells you that L actually is minus X1 minus X2. And now you plug everything in the Podryagin class of M8, of the principal bundle, and you do a little calculation by eliminating basically the second CERN class of E. And then this little calculation tells you up to some factor of half, but then I have a normalized decider. So anyway, these are forms, so you don't worry about torsion. You get that the triviality of this is the same as the triviality of this. And then what you do next, you just plug in things, plug in the various base spaces you have. You have S4, Euler number 2, signature 0, no non-trivial circle bundles over S4. This cannot be satisfied. So there is no way we can find the solution with this. Now, if you put now B4 to be the connected sum of k copies of CP2 bar, then you calculate this, you find that it's 4 minus k. So you get for k equal to 1, you get the vibration I got with a bundle space SU3. So M8 has to be differomorphic to SU3. And then you get another case for k equal 4. But this is not spin. So it's ruled out all HKT manifolds are spin manifolds. So this cannot work. So after all this work and effort, we end up that actually the only case that under the assumptions I've made is actually SU3. Now, if you take the T4 to the action to be T4, you can prove is always a product. It just goes back to the differential equation I proved. I can rewrite the differential conditions like this, something that actually appears in many other areas. So you get the same kind of differential equation. But what I want to stress here is the following: that although we know that SU3 has the left and right invariant HKT structures, and we know that this differential equation has also a solution, it's not clear it's the only one. In fact, I think that it's not clear that CP2 admits a unique self-dual, anti-self-dual structure with positive Ricci scalar, a unique one. So there might be other possibilities, which is have not been explored. So that completes the proof of the second theorem. Well, here I have the other case, but then since there is no time, I will just come to the conclusion. So basically, the conclusion says that, although we have a lot of non-compact examples of HKT manifolds, the existence of HKT manifolds which are strong, the H is closed, and compact is very, very restrictive, actually more restrictive than perhaps what originally we thought. But then, of course, we haven't investigated all possibilities either. I mean, in the case of U1 cos SO3 gives another possibility, which is unexplored. And there is although it seems that it's not a straightforward exercise either. So I'll stop here. Thank you very much.
Thanks, George, for the very nice talk. Yeah, are there more questions?
Yes, maybe. Of these eight-dimensional manifolds, can I think of them, because kind of the structure just looked to me like, is it similar to like a Konishi that is rescaled with like or Swan bundle is rescaled, or no, maybe Konishi bundle rescaled with this phi and then kind of an U1 type of thing over this, or is this entirely the wrong way to see them?
I'm not sure. The answer is it is
Okay.
what is scaled is the metric on the base space, not the bundle itself.
Yes. Kind of you scale the structure coming from the base, right?
Yeah.
Yeah. Okay, thanks.
I just want to make sure I understood. So you're like in this case of sort of characterizing SU3, you're not claiming the geometric rigidity. You're not claiming the structure has to be the flat one.
Well, you see, the ingredients that I have, my calculation is topological, so I can tell you that whatever you get, it has to be differomorphic to SU3.
Yeah.
Now, of course, we know
understand,
there
like
is an HK distraction SU3.
Of course, yeah.
The question is it unique?
Right.
And that depends on the existence of Actually, it depends on two things. First of all, whether this equation that you know very well, the d square on r plus r square plus Ricci square, it might have another solution even in the conformal class of the Fubini study metric. I'm not sure. I haven't looked at that.
Actually, no, now that I think about it, I think I think basically it's sort of a general fact now we know that on a bismuth, so yeah, so on a even on a like Calabi-Yau torsion, strong torsion, if there is a flat structure, I guess it should be the unique. I mean, if it's also bismuth flat, that should be the unique Calabi-Yau torsion metric, actually.
Okay, that well, because the way I done the maybe there is an extra ingredient because the way I done the calculation, let's say if for some mysterious reason I had another undeserved dual structure on CP2.
Well, my proof wouldn't use the like what I'm saying doesn't use the reduction at all, actually. It would just completely happen on the
Okay,
eight-dimensional space.
all right, then there might be another ingredient. Maybe it is a solution of the differential equation, I don't know, that restricts the possibilities because I haven't solved all the equations myself.
Right. Right. And I guess it just so I understand, like there's still the possibility that this that this sort of U1 plus SU2 or whatever action could have like an orbifold quotient, for instance.
Yes.
This is a possibility.
I think if the orbifold is nice, that means a smooth finite cover. Probably nothing changes. But if it doesn't, then of course it's another story.
Yes, yeah.
Yeah, I try to. Yeah, I dealt with principal bundles. I didn't. There are certain complications I cannot deal with.
Sure. Yeah. Well, it's very interesting, nonetheless. Yeah.
So
Are
they are
there
pretty
more?
rigid in that sense.
Right. More questions? So if not, yeah, let's thank George again for the
Well,
very
thank you very much for your invitation again.